Start recording. All right, so I think maybe we should just start here. You guys, the screen share is working. I'm assuming that you guys can see that it says no structures. So just a little bit on the timeline of the course now. So this will be the final content lecture, and then next Tuesday or early in the part of the week, we'll schedule project meetings just to see how projects are going. And then the recitation covering this stuff, I'm going to post later today, and that recitation will be carried out next Friday. And then it's just a quiz and just wrapping up projects, that kind of stuff. So so that's kind of where we are in the course right now. If there are any questions, put them in the chat. This is being recorded, so I assume that other people have a chance to look at this later. So, okay. So let's see how, I mean, maybe we can get through this quickly here. Kind of depending. So we have so we've been covering, of course, databases, and we cover, everything's in a table, and that's everything kind of, you can query it via SQL, and that's fine and good. But the fact is that we have to also ask the question, how do we manage data that has no or very little immediate structure? So it shouldn't be surprising to people that most data out there, so if you look at the data, if you look at data out there, most of it is not structured or ready for a database per se. So, I mean, what do we have? A lot of the data out there is just like text files, just, PDFs, emails, HTML. And then if you want to take a really kind of broad view, it also includes stuff like images, videos, you name it. It could be anything, right? So data, a lot of times when the media talks about a database, or that somebody's database got hacked, or their database was stolen, or whatever it might be, a lot of times what they're really talking about is that someone got access to a file system somewhere and then just kind of snarfled the whole thing down, and then now they have a record of all this stuff that's on file system, and most of that stuff is not databases. Most of that stuff is not structured. Most of it is like text files. I mean, I could put in here also binaries. What can you find on a file system? So that's what most data is. So the thing is it's kind of obvious here, but what we would like to be able to kind of query stuff kind of with meaning. And so what we need to do, if we want to maintain the ability to ask kind of meaningful questions over stuff, we need to kind of somehow structure, or at least envelop it with some kind of structure so we can actually query it. So that's kind of the topic of today. How do we deal with the no structures? No structures are just like just a flat text document. And then the semi-structured, which are things like XML, JSON. I mean, you can argue HTML. You can argue that in some sense, I mean, even straight text files a lot of times have some structure. I mean, there's like chapter headings, subject headings, a lot of times inside of a PDF or inside of a text document. So the blur between structured and semi-structured is it's very fluid. But there's kind of there's kind of this idea of structured data, semi-structured, and then no structure. Okay. And then maybe in the no structure side, you could also add in stuff like images and videos and stuff like that. So, okay. So we want to get to use this data for some purpose. Okay, so there's a fundamental choice here. So and then the first choice is the very ambitious one. It's extremely ambitious, and it was pursued under what's called the semantic web. And I want to cover that because you'll hear about it sometimes, and it's still an appealing vision. I don't think it's really realistic. I don't think it's very practical, and it ran into a lot of problems. But it's worth us going over this to kind of give you an idea of a little bit how maybe people have thought about this kind of general access to loose information kind of problem. So the semantic web is a fundamental choice. And that's basically the vision behind this. And I'll go over it in a little more detail, but it's basically to treat the whole web and all the things on the web. That is the database. And then you have something on the front end that allows you to to query that, and then it goes out and it grabs the relevant data on the web. The more realistic and the more practical, you might say, solution has been this private database solution. So basically the idea here is that you have a database that you build up a structure for. You have some defined tables and things that kind of, there's a point that you're doing this, right? That you have it for some reason. Maybe you want to accelerate your sales or revenue or something as a company, or maybe you want to just collect information on. You want to build a website where you're going to present information like different travel possibilities in one particular region or something. You'll be going out and be grabbing information and then ingesting it into your database, and then your private database, and then providing some kind of front end tool on that allows people to access into the data. Okay, and this can be done dynamically, so it's not like you just ingest it all and there it is, and then things kind of get out of tune. You can be doing synchronization of that. So that's kind of more that's more the practical way it's being done in general. All right, so with those two in mind, let's go into it. Let's talk first about the semantic web. All right, so the initial ideas of the semantic web were developed a long time ago, and they were developed by Tim Berners-Lee. So, Tim Berners-Lee was basically the person who came up with the initial design at CERN for HTTP, for hypertext transfer protocol. So, I mean, he had a giant contribution earlier, and then the idea was that he would. Well, I mean, the idea was that what they were going to do is they were going to take that over toward allowing for people to not just like what happened with HTML was that people were able just to kind of publish and get out their images and their text in a very kind of simple language, HTML, and using the HTTP protocol, and it just kind of liberated all these people from kind of like they could publish, and it really was revolutionary. So the idea was also that maybe they could do that with more things on a more factual level, so that you can have a more finer grain of publication and browsing, et cetera, like that. Okay, so now the team that was led, so it became a very wide effort. The team that led the semantic web idea, they basically had the idea that, and if you look over here, this is kind of like the stack that they're kind of thinking of in terms of how you represent stuff. At the very bottom, we have the URIs and the IRIs. Okay, so and then we have Unicode. So these are really kind of fundamental units. So Unicode, and these are brilliant. So the whole idea of a URI or URL, basically, and Unicode, some way to kind of to basically treat all the world's scripts. That those are kind of the fundamental bottom of that. Now, then we have XML. Which also actually is pretty good in its way. I mean, it's the semi-structured model that we covered in the Database 1 course, if you had that with me, where what we were doing is we were using this XPath and XQuery to access it, kind of like you do with relational databases in your SQL and relational databases. So there was this kind of query language, and then of course that right here we have XML query, so that basically that's our XQuery that we looked at. And then some other stuff about like defining and getting namespaces kind of sorted. These are kind of good contributions. And then XML schema. Okay. So I don't know how many people use XML schema. Some do maybe, but it's kind of getting a little more thin. Then we get up to something called RDF. Okay, and RDF is this idea of a triple store, and we're going to cover that in a second here. Kind of what a triple store is. This is kind of the basis of how information was meant to be represented in the semantic web. On top of that, then we have this notion of what's the system called OWL, for instance, ontology web language or something. Rules, queries, logic, proof, and then we have all this other, we have all these other kind of things that come in. So that's where it kind of gets a little thinner. I don't think this has got much. I mean, even RDF it got a little bit of initial uptake, but it's really not making it. It's not being adopted. So it's really a tough thing we'll talk a little bit about this kind of the social aspects of how you actually would pull off something like the semantic web. But the idea was that people are going to write documents to conform to these, and then what that will allow then is it will allow for a fabric to be able to access all this information through declarative query languages or even procedural query languages, but a query language that overlie the whole web, and then masses of information will be published into the system. So this is like one of the diagrams, and then if you look, you find another diagram. And the problem, one of the main problems with the semantic web is that this is always changing. It feels kind of loosey-goosey, to use a technical term. It doesn't feel like it feels like it's kind of always, it's not really solid and, kind of really stable framework. And there's a lot of verbiage, there's a lot of acronyms. It's a big word, or, it's a big letter soup. Of different like RIF, rule something, I don't know, something format. OWL, okay, yeah. RDF, XML, URI, URL. I mean, okay, whatever. RDF. They have a whole bunch of them. There's a whole bunch of different acronyms that kind of go around, and it becomes a bit troublesome. So let's look at RDF though. RDF, because this is kind of the root of it, and this, I think I will argue, this is kind of the root of the problem, as it were. And I'm hope to kind of show this through this example here. Okay, so RDF triples are basically so the original RDF syntax is all based on kind of an XML type markup, and it is just a nightmare to look at. It's you know, the whole idea behind XML stuff was it was supposed to be human readable and machine readable, etc. But RDF in its original form was just, they had everything was like prepended with these namespace token. It was like, it was a mess. I mean, not a mess. It was just really complicated. And, you know, for people who aren't, you know, like really like, so I mean, it becomes, you know, so, you know, a lot of people, no one wants to look stupid. Nobody wants to look stupid. And you get these people, all these smart people coming together, they're building this big syntax, this giant syntax around RDF. And who wants to be the person in the room who says, huh, I'm just a dummy. You know, I can't follow that. Nobody wants to do that. So all these smart people get together and they're all kind of, yeah, well, of course. And that is always going to be a problem. Because, you know, yeah, I'll get to this in a second. I mean, there's one of the criticisms of the semantic web is they basically said that it's like, see if I have it, I can bring it up right here. It was a good, basically, it's like written by PhDs for PhDs, okay? But yeah, anyways, when you look at the original RDF triples, it was a very problematic. So what happened, it didn't take long. What they did is they basically turned things into this thing called turtle syntax. Okay, so because they had to back off from this XML-based syntax, so they went to turtle syntax, which then gets spelled out or gets translated into this kind of more nitty-gritty XML mess. But that they had to ultimately get around to doing that. And I'll show you a little bit of the turtle syntax here. But let's get an intuition here. So basically, the idea is like this is kind of really kind of the idea of, it goes all the way back to what's called a semantic network. But basically, what it is that you can represent information as triples: subject, predicate, object. So Mike, predicate is CEO, object is this company, and this is my company. All right, and then this company can then become a subject, and it serves, and then, you know, Acme Corp. We didn't want to name customers. Mike, we're going to get back to here, has a hire date of this. You know, this is when I was hired. And that was when I started it. So, all right. So I hope that's clear, somewhat clear about how these, how you can just kind of build out this network of these triples, are basically representing like, okay, from this node in the network, which is the subject, and then put a label on a link, and then to this node in the network. So you can build this, you can kind of build it without having to worry about any structuring. You can build out, in a very flexible way, you can build out lots of information, right? You can just kind of start. I could sit there and say, Mike, hair color, brown, or hair color gray. Well, you know, whatever. All right. So that's kind of the idea behind it. That's the idea. And I think that I went over this in the database one class when I talked about semi-structured. So this is really adopting that via triple store. Whereas XML is a little bit, it's more of a tree-based model. But anyways, in this case here, the way you do this in turtle syntax is you have to have a file that literally has this in it. It has to say the vcard. So what these are namespaces, which are kind of nice. So vcard is one of the namespaces, and anything here with W3 is kind of going to be official. And then we have another namespace. So I can declare my own namespaces, and then based on that, I can always prepend things with a namespace. So in the CPH, which is going to be here, you can find it there. There's going to be your namespace declaration. Get MM, which is Michael Minnock, I guess. And then this vcard then is one of the labels that's in this kind of standard, which is a given name, Michael, family name, Minnock, et cetera, et cetera. So you can wind up building out these triples to represent the information you want. Okay, so that's kind of RDF as the basis of the information. Okay, so now what we have also then is we have, and now this came along a little bit later. So I mean, one of the problems is these things are always evolving. But then Sparkle comes out. Sparkle. All right. So now we have a query language then, which looks a lot like SQL. That's good. And it's like this. It's like saying, what is this thing right here? It's saying, give me the first name and the last names of people, right? Person. So that's a variable there. Person is a variable, right? Because it has a question mark in front of it. It's a variable, right? And then it's using this work set from the CPH namespace. And then it's using from the CPH, this CPH token, which is this C phrase company. Then it's basically saying the person has a given name, F name, and that's part of our answer there, and a last name there. And then the person has a hire date, and then the hire date has to be less than 2020 0101, right? So you can see here, this is a declarative like SQL like syntax in a way, right? And it's nice because you have variables, HD here, which is not part of the answer here. And then you can actually go and you can solve for this over, over what? Well, over a triple store, okay? Because, this won't solve itself. It's got to be done over a triple store, right? So, there's going to be an engine and all this other stuff. So the way I'd like to think about this is like, wow, triple store, maybe we could probably translate to SQL and have a database doing this under the hood. But I think that a lot of people built their own engines or whatever. So Sparkle engines get built. So they're kind of building the whole kind of parallel type of query evaluator that we see in SQL. And remember that the database, in this case, the database is conceptually at least, the database is a single table, which is a single triple store, right? Now, there was some work that was done that basically changed that in some interesting ways, where you actually get more tables than that. But let's just kind of think about it conceptually here for the time being. Okay, so you can see how this would start. This is basically to give all the people first and last name who work at the company that were hired before 2020 0101. All right. Okay, I hope that's clear. Now, let us consider the following problem. All right, let's say that we have a database here. Now we have this database here is representing a trinary relationship, which is suppliers, products, and customers. Actually, it's quaternary. It's supplier, product, customers, and year. So who's the supplier of what product to what customer in what year? And that's a fairly, okay, so this is really using the power of kind of relationship. This is a relationship. This is modeling the idea of this relationship that's just kind of complex temporal relationship between two parties and products that are being exchanged between them. So it's actually there's a fair bit of representational complexity here. So now let's say, and this is a real Achilles heel now. So let's say that we want to say, so a lot of times you go to somebody and say, hey, and I had a lot of conversations with people because I was this kind of, I was around some of these people who were developing this kind of stuff. And I was a bit of a thorn in their side because I was just like this, I was a young but grizzled relational person. Grizzled in the sense that I had gotten some advice from my advisor when I was at university about this stuff. And it wasn't me that knew that, but it just basically, there was a lot of like skepticism on my part. So I always would come and say, well, how are you going to deal with this? And they would first of all, look at me like I'm an idiot, which maybe I am, and that's fine. It's my right to be an idiot. If that's what I am who I am. But they would look at me and say, well, no, what are you, dummy? We can reify this. So, all right, so we can reify this, which means basically we can, you can do this way. You can say, okay, we're going to give IDs to each of the tuples. And I'm already sitting there saying, doesn't that kind of break like value orientation in relational databases when you do that? But okay, I'll let you do that. I'll let you put a surrogate key in and just have a single attribute key. Fine, not a problem. I'm accepting it. Okay. And then what we're going to do is we're going to basically then reify the relation. So we're going to take this relation, we're going to reify it down and represent exactly what's in it. So we're going to, reification is like, it's a big word, whatever. But basically what it does is basically saying, we're going to pick this thing apart and we're going to basically take it like an X-ray of it, snapshot, and we're going to re-represent it. So we're not going to lose any information. And that's true. You don't lose any information. So let's see what happens here. What I say then is I say something like this. I say, okay, the subject is this thing called 1. And then the predicate is supplier, and that's IBM. Then it's got a product, that's DB2. And then it's got a customer, SEB, and it's got a year, 2019. And we do the same thing with the second tuple and the third tuple, right? Okay, so I hope that everybody sees that you can capture the information. So you've not lost any information here. We've just reified this n-ary relation. So this is an n-ary relation that we've now reified into a triple store. All right? Sounds good. All right. Now, think of it this way. We want to write a query. Give us the companies that were supplied by Microsoft after 2015. All right. So project customer, where supplier equals Microsoft, and year is greater than 2015. It's a pretty straightforward query, relational query. That's an SQL query that's just basically going over this table. Very, like, that's not hard. All right. So I would beg you, and we're going to do this part of recitation. I want people, can you write this in Sparkle? Can you write this in a query language over this thing here? Can you write the same query? This query over this thing is really like direct, right? Boom, you got it, right? It's done. That same query over a triple store can be done. And well, we're going to see later in recitation what it looks like, what that monster looks like. And then your question will be, well, maybe I can define views. Yeah, maybe you can define views, but then you've got to have a really solid view mechanism. But basically what it's done is, it's by reifying everything, you've really kind of like complicated a lot of the basic access that SQL gives you. So it's not as compact. The language is, something had to give. So what happened is the queries kind of blew up because the representation system shrunk down. All right, that's essentially what happened. Okay, so we'll and then, you know, people can debate now, what does that mean for practicality? And the answer is, well, a lot. And is this kind of the Achilles heel of the whole system? Yeah, I think so. Anyways, so the idea though is you model things on triple stores, and then you have these rule systems, these quote views that work over them. But these views are like, the views are always like giving you, they're not giving you out n-area relations. They're always giving you out things in a triple store. So it's very awkward to kind of work with these ontologies. And then you have these kind of rules over them. And I don't know what they're saying logic in there is. Logic. I mean, there's a long story. I can tell you why these were attractive. There's attractability. It's a lot of attractability reasons. I mean, when you go down to logics that are only basically over the restricted number of variables in the logic, basically is what it's doing. But basically what it's saying is that it's called L2, I think. That's how it's referred to. You get a lot of properties out of logic. There's a lot of things you can actually do when you're restricting yourself down to that kind of logic. But the problem is that you can't represent like temporal relay. You lose so much ability to kind of represent things we need to represent. So n-area systems, relational systems are n-area systems. So in some sense, the whole enterprise here hobbled itself by basically just saying, oh, we're only going to be looking at these this fragment of logic. We're not going to allow for true n-area relationships or relations. We're going to reify them instead, and it doesn't work. Or maybe it does. I mean, maybe it will be solved. I mean, maybe at one point they're gonna pull a rabbit out of the hat, but I don't think so. So it's a real problem. All right. So the status of semantic web. Okay. So let's back off a little bit. Okay. So if the semantic web, and trust me, after the amount of money they've spent on doing stuff working in this area, they better figure out a way to back off and kind of save face somehow. I don't know. But anyways, you know, well, I mean, I'm not against that. I think it's good for research and all that, but anyways. Okay. So semantic web, okay, using the web as a quote database. Yeah, so arguably the crawling and PageRank, right, Google, is in the spirit of the semantic web in some sense. So maybe that's a good way to crawl it off. They started in the late 90s. The main standards bodies, URL is XQuery, XPath, XSchema, Sparkle, OWL. All right, then they went to this DBpedia, Wikipedia. Okay, even Google now is doing this thing called knowledge graph. So Google is, I don't know much about this, but I think what they're doing is they're basically defining one of these kind of common sense kind of graphs of kind of like, well, it's never really written anywhere, but you know, a dog is an animal, you know, animals have finite lifespan. I mean, there's this idea that there's this kind of common sense kind of relationships among these kind of basic things in the world. Knowledge graph is kind of, I think knowledge graph also does with factual stuff though also too. It might say something like American Airlines is an airline. Maybe it was founded a certain year. They're going to curate a giant graph of knowledge of common sense facts, or you know, and maybe that's the best way to do it. Maybe to do it something like that. But then Yeah, and it can be, I mean, I have something against that, but I just think that it's going to be tough for them to represent really kind of temporally intricate things, like this customer called me about this particular topic at this particular time from this particular area or something. It's like, it gets very difficult to kind of represent that kind of stuff. So it's okay. So basically, it's an admirable vision. I think I still think that it was an admirable vision, but it's very challenging because imposing workable semantics across the web is difficult because people have to like. All right. It's actually difficult to work with the ontology technologies and standards. And this is where the criticism is, like, written by PhDs for PhDs, and they have this really kind of a certain style that is really, I think, a turnoff to people who are just want to get stuff done. And so when you do that, people have no problem ignoring things these days. If it doesn't kind of immediately hop off the page and start solving their problems, they're going to basically do something. They're going to go, do something else. They're not going to, no one's going to, I mean, maybe some, like the PhD types, but it's not going to get much legs if it's too difficult to deal with. And it was, and is, I guess. So scalability, interoperability problems in alphabet soup. So yeah, the scalability, there's also a lot of scalability issues. I mean, let's not even talk about like things like transactions for now. Like distributed transactions are just a mess. So how are you going to like deal with? So like they had all these ideas, like these use cases where you get these kind of, you're supposed to have these agents that were out there doing stuff on the web, like these artificial agents that would go out and do stuff on the web and kind of crawl through all the stuff and then serve you stuff and then book things and do all that stuff over just general web. Yeah, I mean it's really difficult. I mean, so interoperability. Semantics based on triple storage verification is actually weak, unworkable, uncontrollable. Yeah, so that was the thing I tried to show earlier. It's still up to debate. Somebody might say, well, no, it's not that bad. All right. So yeah, so basically, I don't think it's going anywhere, unless I'm living in some alternative universe where I don't see this it going anywhere. So now I feel like I pay some attention to what industry is doing. So I don't know, maybe. Usually when people do something or when groups are doing it, it's usually some kind of big, kind of more like public sector entity who's trying to kind of like, I mean, I think one of the problems is they put so much money into it. So you get a lot of people who like put all this money into the semantic web stuff, especially in Europe, I'm afraid. A lot of people funded it. They really funded it. So now they've got to like leverage it and get people to use it, damn it. And, it's not a good place to be. And that's exactly, I think, where they are. So, this is probably why I want to make the video private, because I don't want to unnecessarily create enemies, but then again, I don't really care. All right, so that's plan A. And plan A didn't, maybe. I'm I hope, I want to be wrong, but, whatever. Let's go to plan B. All right, we're just going to ingest into our private database. Because we're just a small entity. We got, time is money. We got to make this thing work. We got our customers. We want to serve them. We don't care about these big standard bodies. No. It's like time is money. So now we got to make it work. Okay. So a more decentralized approach where the organizations ingest data into their own databases for their own purposes. Okay. It relies on a mix of, at least I'll give some terms here. So data exchange, data extraction, and bulk loading of document or bulk loading of resources. I'll kind of more generalize it to say that. Not necessarily based on relational databases, though that is the assumption here. I think that's generally how you're going to do it. I think that's kind of consensus now, that it's going to be done in relational databases. Nothing else works. So yeah. So all right. Well, unless I'm wrong. Somebody tell me. All right. Okay. Of course, the thing is, we can still use a lot of what's going on, what came from the the W3C, the World Wide Web Consortium. So the Unicode and URLs, yeah, absolutely, that stuff is really good, right? That allows for this kind of we can link to stuff, right? So there's nothing wrong with that. All right, so here's like maybe a kind of architectural diagram, which is not the prettiest thing, but it kind of maybe will give you a sense of kind of the overall universe of this. So here's the relational database up here. And when I say the relational database here, what I mean is this is the thing we want to actually, this is the thing we actually want to work with. This is our private database that is serving some task. And then we have some other relational databases, and data exchange, in many cases, what we talk about data exchange, that's something that kind of brings this relational data into our data. So we talked a little bit about this with data lakes earlier, and we talked about, and I'll just briefly mention this in the next slide, kind of just to refresh on kind of how that works. But that's not really the topic here. The topic here is to deal with things, okay, that are a little bit no structures or semi-structures. So we have CSVs, Excel, and Sheets. Okay, Excel and Google. I think Google Sheets. Okay, this is, there's a lot of people. This is actually a big complaint people have, is that there's a lot of people who are really good at spreadsheets, and they just want to keep everything in the spreadsheet. But spreadsheets are really difficult to kind of you know, you can't run like big operate. I mean, spreadsheets have their uses, but there's like a lot of people who work on the database side are just like, they feel like, well, they want to slap around the person who's like really fixated on their spreadsheet. So the people, oh, I work in my spreadsheet. I'm gonna do all this work. Okay, now I've updated in the spreadsheet. Why? How? Now, can you update that in the database? It's like, oh, yeah, we can take it in again. Or even worse, they download stuff from the database. They work in a spreadsheet and they say, how can I put this back in the database now? So okay, there's ways, but I mean, spreadsheets are okay. You know, they're a fact of life. Then we have XML and JSON, which are kind of more semi-structured formats. All right. And then we just have like your just kind of no structures, your PDFs, they're just any kind of thing, HTML, which is any kind of thing, or just your text files, which are any kind of thing. And then I suppose you have your binaries, but we don't have to do with that. So here, let's images and videos. All right, so you can have major, like you can have machine vision, you can have all this other stuff that's actually trying to kind of bring these things. You can bring these things into the database as a binary large object. You can keep them outside the database and link to them and do analysis on when you bring them in. So we don't know. There's lots of special specifics for that kind of thing. But what we're going to focus on here now is just kind of like working with CLOBs, character large objects. This other stuff is, of course, quite interesting. But I mean, there's always a question of like, when you work with stuff, and this will come up in a second here, does the main kind of processing to lift it up to something structured, does that happen outside the database or is that happening inside the database? All right, so that will be a kind of a theme. But basically we have two types of tables. We have the model table. So the model table is like, yeah, we've gone and we've, you know, we wanted to get contacts or something. So a contact is a model table. And we went through all this HTML and all these things where we were like looking around for people's names next to an email. And then we were able to kind of like put that in, turn that into a contact. And then we did on the outside here, we actually went and we, you know, in the load program, what we basically did is we did this analysis or this extraction, and then we loaded it into the model table. Alternatively, what we could have done is just kind of chuck the whole thing into a document table. So this table right here is just the actual character large object content of the associated document loaded into the database. So those are the two avenues into the database. And we'll talk about both of those. So what we're going to cover here is we're going to cover data exchange, just quickly about like data exchange, data extraction. So extraction is like we're going here, we're pulling out stuff and putting it into the model table. Bulk data load, all right, so that we were going to load them in here, and then the extraction or analysis part is actually going to happen inside the database. And then a more general problem that we're not going to really we're just going to kind of skim to kind of give kind of a sense of where things are, but just like the bringing in the full kind of machinery of natural language processing into this to do. Because this, I mean, these are written in natural language, and then maybe we can use some of that technology to kind of ease this process. All right, I don't see any questions here. All right, so data exchange. Okay, so so the legacy relational database is just dumped into the data lake. So lake is just something that means it doesn't really have much structure in it, but we just kind of like dump it in there. And there's kind of two different views of this. There's the ELT, which means to extract the data, all right, which means grab the data, load it into your database, and then transform it once it gets into your database, versus the extract, transform, and load. This actually is kind of similar to this right here. So this right here is this data exchange problem here is just, well, it's kind of like where's the kind of analysis or the transformation of the data going to happen? Is it going to happen outside when you're like right here, you're doing kind of the transformation outside the database, and then you're just kind of pushing it in. In other cases, you're bringing the stuff in and then you're actually doing the transforms inside. So the same thing happens with data exchange. You could have like a special wrapper here that goes and it like pulls out the right data in data from this database suited to your purposes, and then puts them into a specific model table. Or you can just take the full table here, dump it into the database, and then have a cascade of views that will transform that into what you want your model table to be, right? So that right there exactly is this ELT versus ETL. Okay, so are you going to do is the wrapper going, so you're going to extract it, then transform it, and then load it into the database, or are you going to basically extract it, load it into the database, and then do the transformation inside the database? So the ELT is kind of more the modern way of doing things these days. All right, so this DBT tool, the whole 5tran tool or approach are kind of arguing for that as the way to do things. The ETL is just like the old-fashioned way, but even 5tran is doing ETL, you can argue. So companies like, there's a company called 5tran, which actually what their main contribution is, they build standard wrappers. So for instance, if you have like, what they can do is they can have, I think they have wrappers for like Gmail or something. So you can basically take all your Gmail and you can snarfle it in and boom, it's in the database. Or you can do the same thing with other apps. So they have, I think, like several hundred different systems and apps that they actually built these wrappers for that will will bring them into your database. It will bring it into your database as kind of nice structured model tables. All right. So you can imagine that's quite useful. So the argument is that the argument from an industry point of view is that you don't write those wrappers yourself. Go and pay It's much more cost effective. Having your own development team write those wrappers, if it's like for standard tools, that is crazy amount of money. So you're better off going and like buying that from a team that's kind of always dedicated to kind of keeping those things up to date. Unless you're El Cheapo, and then you say, well, I can just do it myself, and then you just do it. Or you have your own specific things that you work with that 5tran that are very bespoke or custom to your own environment, and that you don't 5tran is not going to have a wrapper for that. Okay, like 5tran is probably not going to have a wrapper for Canvas. Okay, if you wanted to do a data export out of Canvas, you're probably going to have to go and do it yourself. Okay, but maybe they have one for Canvas. I don't know. I mean, but they're going to have them for more and more. So people who like these wrapper producers are probably good to use for that. All right, so data exchange. But the data exchange we're going to talk about more is then you have data exchange for like XML and JSON, and then these other data exchange is kind of like data exchange is that you already have it in a structured or semi-structured form. You're going to bring that into the database. Okay. Data extraction, however, this is kind of what we want to focus on mostly now, is we're actually going down into the actual text and we're going to pluck things out of that text. And with that, we have the centrality of regex. So I'm assuming a lot of you guys have had experience with regular expressions, and in recitation, you're going to get more. So we're going to have regular expressions are going to be are really kind of a central part of this. I should also add here that there's lots of other, so depending on where you're doing it. So if you're doing it here, you're doing the data extraction here, usually this is not being done in the database. So you have the use of like Python, let's say. You're going to use Python, so you can use regular expressions, POSIX regular expressions inside of Python. Or you can use stuff like Spacey. There's a library which is really good actually called Spacey, which does some of the natural language stuff. So we have two essential ways that we actually go down and we work with the actual flat text. Two essential ways. One is using regexp. The other one is using a little bit more natural NLP, natural language processing stuff, that is doing things like stemming things. So that you can get you can generalize a little bit with your verb forms or your plurals and singulars. Okay, so it does a lot of that for you because you don't want to be doing all that stuff with regex. That becomes a bit very much burdensome. And then we have natural language processing. So let's go over this. Let's try to talk a little bit more specifics here to kind of give you guys a sense of this at least. So if we have external programs that are doing like the ETL, so they are doing ETL because before they load to the database, they're going to be doing the transform. So they're going to load model tables into the database. So we have stuff like pandas, which basically what it will do is it'll convert the CSVs, which is you can always convert all of your spreadsheets into CSVs. Of course, you might say, well, but I had this really weird spreadsheet where I have things set up that they're like doing cell calculations. I have put in numbers here and I do a cell calculation over here, and those reflect over there. Yeah, that's really hard to import into a database, right? That's really hard to import into a database. But so you can't you can't just basically, so there's a lot of weird stuff in spreadsheets that is not really importable, because it basically winds up being essentially a workflow, or it winds up determining a flow of numbers through a cascade of calculations. And you're gonna have a really hard time kind of bringing that in any principled way into the database. So yeah, good luck with that. But if you can turn it into a table, a lot of spreadsheet stuff is just tabular. So with that, you can use something like pandas to convert it to data frames inside of Python, or JSON, okay, or data frames or JSON, and then you can traverse it inside your Python program, and you build up your insert statements, and then you do the insert. Or just a terminology here, there's something called an upsert. So a lot of times what you do is you upsert stuff. So what is an upsert? What an upsert is, it's an insert if the thing doesn't exist up in the database, or it's an update if the thing exists up in the database, but there's a slight change to it. So you basically are doing upserting. So if you're going to have synchronous, if you want to keep things synchronized, it's basically a set of upserts that you're doing into the database to keep the table fresh. All right, what do we got here then? So so here's just kind of like a little bit of Python here, how you would go. Okay, what is this? This right here is basically, you get a response back. So there's all this stuff like, and I think that probably a lot of you guys are doing this for your projects, is that you're calling things like SMY, the weather people. And so you're making a call in, and you're getting back JSON. So you do stuff like this. Okay, JSON loads, and then you basically can then just traverse the JSON and then build up inserts. So you just do that through just basically a request, and the URL you're sending in here is the REST call in to the API to get back the JSON. All right, or get back XML. That could also be. You get back XML or JSON, which typically will get passed back. If XML gets passed back, or if you have XML files, then you do something like basically, like for instance, the XML at system will log it. You use this, you basically, you go up and down the DOM, the document object model, and then you snarfle up and you grab all the data that way, right? So you're gonna grab the data by traversing the document object model. So this is a simple example here where you're going to go, by the article tag, so you can go and find all the different poisons that they have at System Below. All right, data extraction now. Okay, so now we get into something a bit more. Now we're going to get a little bit more nitty gritty. Now we're talking about stuff like PDFs. So you got a big PDF. All right. So PDF, there's a tool, at least in Python, called Textract, and you can use Textract to go in and decode it and just pull out the full text, of the thing, and then over that text, then you can do this. You can do regular expression searches. Okay. So this is no structure, just kind of coming in as flat text. Table of content. Then also you have table content inside those. So you can get something called Tabula, which is really nice. That will bring out those tables. So, I mean, the extent, I guess, let's back off. Let me just kind of be all inclusive here. You have also something like Textract. I can't remember what the name of the Amazon tool is. So then you have the whole issue of just using OCR, object character recognition, where you're going to be loading in kind of printed documents and pulling out the text. So yeah, that's pretty impressive now. I mean, that actually works, if you can imagine. So you might actually be like pulling in actual, that's really, that's a real task there. So okay, but I tend to hope that everything is already digital. So anyways, but then there's another tool that I could recommend, and that is the thing if you want to like grab and snarfle up HTML, and that's this Beautiful Soup library. So Beautiful Soup is kind of very similar. You have this kind of little query language where you can kind of go in and you can kind of pull out. You basically get you're basically, it's not as nice as the document object model from XML, but you're able to kind of go around and do some querying and searching on HTML. You get into the whole kind of extraction process through that. Then you've got a lot of tricks you have to play, because a lot of times the people, I mean, I think the way people work in this area is that it's a constant battle between the person who has a website who wants to open their information up to search engines for search engine SEO, search engine optimization, because they want to to bring in people to their content, and then you have the people who want to grab and hork that content. They want to snarfle it up for their own purposes. So, and that's illegal, of course, illegal, but it's still a wild west a little bit about this stuff. So you have this arms race of them trying to kind of put security stuff on top of that. But we know in principle, it's very hard to protect something that you also want to provide, but there's a whole bunch of tools that go onto that, with the CAPTCHA and all that stuff. I mean, there's like all these stuff. Yeah, it's a big arms race. So, yeah, I'm probably telling you guys stuff you already know, but why not? Let's see here. I'm going to get to a point where we're going to get into something a little bit technical now, or not, I guess I'll ask you guys, we don't have that many people here, so I can just ask you guys, just a quick hands here or vote. Should we muscle through or should we take a break? I mean, I think it'll be more time efficient, I think, for all of us if I just muscle through. Does anybody want to take a break? Hands up if you want to take a break. Let's just muscle through. We'll get this thing done. All right. So bulk load. So the other option, of course, back to this thing right here, is to do the bulk load. So we're going to take all this stuff and we're just going to bring it in, and then we're going to have special tables here, which are going to have all that character large object content inside the database. So we're going to let the database do a lot more of the analysis. So this is definitely an option. So basically, yeah, we're going to bring in the text, the PDFs, the HTML, etc., are going to be directly loaded into the document table inside the database. Or you just have like these kind of large character objects. So you might actually have it in your database already. You have like a description field, or you have an entry field where like the physician or whatever has a whole bunch of notes, right? So you already have text inside your database where they're putting in notes, right? They're typing in notes, or so. In that case, we need to have regular expression or this full text search capability within the database. And luckily, PostgreSQL has both of these, and that's what we're going to go over. There's another thing I just wanted to mention on the bulk load that I mean, typically there's something called sentiment analysis, which it's very, very useful. And the reason why it's useful is because, sentiment is kind of like, do people, well, is this, okay, I've written a review of something. Is it a positive review or a negative review? If you see a lot of words like crappy and sucked inside the review, it's not necessarily. So this product definitely was not crappy, and I would say it didn't suck. And then I go on, it was actually quite adequate. I mean, but that'd be a tough thing for sentiment analysis to do. But basically what sentiment analysis is doing, it's usually based on some kind of machine learning model where you can have a whole set of examples of really positive reviews, a whole set of examples of really negative reviews. And then you build up this model that can determine is it positive or negative. And then as real reviews come in, you can then label them positive or negative, right? And that's useful because, well, I mean, one of the problems with reviews is that people fake these things. All reviews are fake, or not all, but many are fake. So that's another thing you want to determine. Is this faked? Is this kind of just like, artificial kind of being complimentary, or is this seem to be a genuine story? I don't know. But anyways, this idea of kind of putting the sniff test on the actual text coming or the actual content, saying is this, is that, is it, I think people were like looking at like, okay, what can we, based on the writing style, what can we infer about this person's demographics or their values? I mean, it can get pretty creepy, right? I mean, the whole sentiment analysis can get real creepy. That's not really my department, but it's more just kind of a question of the technology that would do sentiment analysis, mostly based on machine learning and giving examples. Oh, good. So I see somebody said yeah. I think since no one objected or no one claimed they want to break. If anybody wants a break, just say so. We could take a 5-minute break. But again, since it's Zoom, I mean, if you need, you can take the lecture into the bathroom. I mean, just don't keep this as long as your video's not on. But
anyways, I'll shut up. Okay. All right. So what am I going to say here? Yeah. But so there's this kind of side thing, like doing some of these kind of more advanced things, just to keep in mind. All right. So and you're probably not going to do that inside the database itself. You're probably not going to have the database engine itself doing sentiment analysis, but nothing says you can't. I mean, nothing. But my understanding is that these kind of things are offline, kind of getting Postgres. I mean, I don't know if it's really much of a point in doing that. I think that it's always kind of a fine trade-off between what am I going to do in Python, or with these extra really nice, fancy, easy to use tools, and then what am I going to get done in the database so that at query time I can add support for stuff. All right. So now we're going to talk about regular expressions. Now we're going to talk about something concrete. So regular expressions are pretty fundamental, and this is one of those things where I know that, like, if my company ever really kind of started rocketing, I would, if I was giving an interview, I would probably give a regular expression problem, because if a computer scientist doesn't know regular expression, that's bad. You got to know regular expressions. I mean, that's an interview question, definitely. Something simple about regular expressions. This stuff you need to know. And I'm assuming a lot of you guys already know it, but I mean, the reason I'm including it here is because this is need to know. Absolutely need to know. You need to know this stuff. All right. So regular expressions in the theory class is pretty weak, but then more practical, we're developing the Unix work, and then it was slight variations and whatever. And then POSIX is kind of that's kind of, you want to kind of go to the POSIX standard. So both Python and PostgreSQL conform to this following POSIX syntax. The dot matches any character. The caret matches the start of the string, but as we'll see, the caret is overloaded, and we'll see where that happens. So caret has a special meaning too. $sign is going to match the end of the string. Star is the Kleene star operation, mathematics from Kleene. Star meaning 0 to an infinite number of times. Plus is 1 to an infinite number of times. Question mark preceding the regular expression is I'm sorry. Question mark not preceding, but the expression preceding the question mark can appear 0 to 1 times. And these right here, the star question mark plus question mark, are the non-greedy variants of this. So they'll match as much as they can, whereas the greedy version, which is most of the time is what you use, matches it. At least it can actually match. All right. So greedy, non-greedy. Actually, maybe I got that reversed, but anyways, I mean, so non-greedy, greedy will match as much as it can. Non-greedy will match as little as it can. The first thing that it'll match. So anyways, I tend not to use the non. I tend to use the greedy until I realize that this isn't working. Then I have to kind of use the non-greedy. Open brackets preceding matches m times, and then we have an m to n greed and then non-greedy variant. Okay, escape special characters. So if you want to match something that has a $sign, you have to escape it. And then the square open bracket, closed bracket indicates the set of characters, A, B, C, D, so it'll match either A or B or D or C, D. So, and then if you have a caret in there, it will match anything but A, B, C, D. So the caret inside of the brackets has a special meaning that basically complements what's being specified in the bracket. All right, we have OR specified by the pipe symbol. And then we have, these are the important ones here. We have the open parenthesis. This is usually where people have the problem. This is where people usually need to learn. You have the open parenthesis and the closed parenthesis. What this does basically is this is how you actually grab something from a regular expression. Because a lot of times it's like, does it match this? Yes. And it's like, so what? I want to grab what it match. I want to grab the match. I want to pluck out something, right? And the way I'm going to do my plucking is with these parentheses, right? So the group can match later. Okay, and then once you pluck, then later on you have on other calls, you can actually do \1 for the first thing that was \2, set \3 to get the group. So what this is doing is it's actually doing what's called capturing groups. All right, and this is the same kind of thing, but it's non-capturing group, so it doesn't capture it, but it does delineate it as a group. All right. This actually is quite useful, and it's just to kind of build up, like you want things to match. Well, we'll come to that later. All right, number matches. Okay, these are some special things. Matches the contents of a number group, anything that's a number. A D is a digit. Capital D is the non-digit, so the complements get done by capitalization. Don't ask me why. White space, non-white space, word character, non-word character. Okay. All right, so let's just say, so if we say something like this, so in Python we say import RE, regular expression, and I say in RE I'm going to do an RE find all. So I want to get all the groups that are going to be matching this. So again, this is a group. It starts with an M. Then it has any number of word characters, right? And then it has an E, right? And then it has a space, right? That's a space right there. Okay. So what this is going to do is it's going to go through. It's going to say, okay, that doesn't match, but this doesn't match because it's not like ending with an E, but Mike does because it matches the M, and then it has IK for two different words, and then it has E, and then Martine also matches, and Billy doesn't. If I had me in there, that would match, right? And then what it does is then it basically, well, it just, since I was putting it into groups and it's finding all the groups, what it's going to wind up doing is that then it just, it'll actually wind up being Mike and Irene will plop out of this thing, okay? So that's kind of a simple like use of a capturing group inside of Python, right? And then all this other stuff, you can do all the other ones inside of Python. Use all this other stuff. You can play around with these. Okay, now the like and the I like is a case insensitive like, I believe. These are like the old fashioned way SQL did it. And these are really kind of not really, I use them sometimes. I mean, I shouldn't, but I do because it's so easy just to put like in there. But really what you should be using inside of PostgreSQL is the tilde operator, which is fully POSIX compatible. So let's use that. Let's try to use that. So here's that simple table, document, and it has like ID of the document, and it has the full content. So this was the result of a bulk load. All these documents got loaded in bulk. All right. So give me the ID where the content matches Trump. All right. So, and this is capital Trump. All right. I'm sorry, I should put like if you want to make it case insensitive, it'd be tilde star. Tilde star is a case insensitive version of this. So really this actually is not going to match anything because Biden and Trump are usually going to be capitalized the first letter, or it's going to match very little. What you want to do is you want to put a tilde star there. What a star. Sorry about that. So it's like always this little fiddly syntax, but that's the way it is. All right. So this right here will give us the IDs that are matching, where the actual content of the document has Trump in it somewhere. And this will give us where it has either Biden or Trump. I'd have to put a star there to make it so that it work, because it would be uppercase, lowercase. Okay, so but that's not very useful because that just says, okay, they were mentioned. But now this is actually what's more useful. So right here, what this will do is this will pluck out of the document each sentence in which Trump is appearing. Well, this isn't quite, this could be kind of made a bit more sophisticated so that Trump actually, in this case, Trump has to appear not as the first word of the sentence, or not the last word of the sentence. But we could actually extend this relational, we could extend this regular expression so it actually could do either of those, right? So that it could basically have Trump as the, but notice here, it's got, and it can't be the first sentence of the document, and it can be the last sentence of the document, but it can't be the first because there's a period there. Or is that true? No, it'll match the first. Basically what it's doing is it's saying right here, it's saying match any set of words in the document as long as they're not a period. So what that means, it means if we have somewhere we have a period and then we have a space and then we have a sentence, it's going to start matching right at the end of that period. It's going to start matching there, and it's going to go across. It's going to scan across, taking any character until it reaches space Trump, and then it's going to basically scan where all the characters that are not periods, that are not a dot. I don't know if I said that correctly before. They're not a dot. They're not ending a sentence, but it's going to scan all those out until it comes into a dot. And then when it comes into a dot, it's done. It's going to do basically a caption group over all that. So what this essentially is doing is it's grabbing out all the sentences in which Trump appears, right? All the full sentences in which Trump appears. I hope that's clear to people. And it's giving the ID of the document too. So, okay. So I hope that was somewhat clear. All right. So that's using, and then you can replace too if you want. So if you want to go through and get out all the, basically what we're doing here is we're going to get out all the content where we're replacing Trump with the orange one. All right. Now, that's like pretty low level stuff. This is and I think the argument is that you don't want to do too much stuff that gets so low level inside of regular expressions because it gets very, very fiddly, as they say. And it also neglects some really simple kind of linguistic support. So inside of PostgreSQL, it's not completely developed, but you can add on top of it. There's this full text search capability. And what we can do here is we can implement the kind of so let's just maybe examples is kind of like how we can go about doing this. All right, so what this function here to TS query, that means what it's going to do, it's going to take an expression here and it's going to turn that into what's called a text search query. This function here is also going to do it's going to turn it into like basically a text search vector. And this double at is a special operator defined for those types. So let's go here first and let's just look at kind of what these things do. Now, if I say to TS vector of the following text string, the text string is King Kong Bundy was a great wrestler. It is sad that he's no longer with us. You rocked, King Kong, RIP, okay? Now, when I push that through to TS vector, this is what plops out. So notice what happened here. King is a token, so it tokenizes the whole expression, right? And it not only tokenizes, it also basically stems. It stems Bundy here. Bundy gets stemmed down to B-U-N-D-I. All right, now that was a mistake. It shouldn't do that. But if I say something like, you rocked, King Kong, when you take rocked and you stem it, it takes it down to a rock. All right, it plucks off the ed, the ending form, and just stems it down to kind of what linguistically it represents, like this is the lexeme of so it's stemming it down to kind of a core meaning unit for that word. Is it going to work perfectly? No, but it's going to be helpful because you wouldn't want to have to write the regular expression that went and did that. Okay, so this will deal with all your plurals and your conjugations on verbs. Notice here that it's taking in the language as an argument. So it would be different if you put in Swedish. Swedish would take off the ARs. Swedish, they have a different rules of their language. All right, so you can get access to different languages there. So anyways, the TS vector winds up being this thing right here. And what it's telling you is it's telling you what token number they are, where they appeared. So King appears at 1 and appears at 20, right? Okay, and then Kong is at 2 and 21, right? So basically, this is kind of giving you, this is giving you some positional information as well. That's what a text string vector is, right? So when you write a text string vector index, you're basically it's going through a document is building one of these. This becomes the inverted index, if you will, of the document. Right? They call it inverted index in information retrieval. Now, the TS query, that's another function, and that basically takes in this query here. Trump, see the ampere, and presidents, all right, and that's, so president right here is in the plural form here, and then tweeting or yelling. I mean, say what you will about the whole Trump here, but I mean, oh, just crazy. It just became entertainment, I suppose. But anyways, we'll get into it. Tweet. I got a call coming in here, which I'm going to call back. It's not a spam. Anyways, they'll leave a message if it's important to leave a message. Otherwise, All right. So notice here what happened here when we went to TS query. It did the stemming as well.
Okay, so presidents, actually the plural here went down to presid. Okay, so yeah, that's weird, but anyways. But tweeting got its ing, and it's yelling got its ing pulled off. All right. So what this allows for that is, so the idea is it's pretty simple here. What's going to happen when we do the matching now? We stem them, and in stemming we're generalizing, right? Because a whole class of different documents would or queries would get pushed down into. I mean, we're generalizing in the sense that what we're doing is we're taking away these kind of distinctions at the morphological level of the language, and then we're more likely to get a match based on that. Okay, and then the actual matching logic is pretty straightforward in the sense that what it's going to do is it's going to say, does the document have Trump and president? All right, it has to have both of those in the content in the building up of this index. So one sec here. I just got to make sure see if they actually did leave a message. I just have to check this because it could be something that I need to respond to immediately. It's possible. And okay, maybe I need to call it back now. Okay, it's not that big a deal, but anyways, I can continue here. All right. Okay. Or Trump president. Okay, yeah, and I think that what we're trying, this will give you the exact same result. I could say Trump president and not tweet, or I could say Trump presidents and not tweeting, and they're going to collapse down to the same match, or the same full text query search, or full text search, text search query. Okay, now full text search. Okay, so the documents get tokenized. I think I already showed this here. Okay, yeah, so there we are. Now, indices. Okay, so indexes. Here's kind of a simple way to look at the way that these things get indexed. So if I consider this, so the index actually, what it winds up being, the indexes in this case wind up being pretty big. All right, so it's not really pulling out. It's like, how do I say this? It's like if I'm searching, I'm not going to be able to escape searching every single index entry here. They're all going to be touched, but they'll be resolved very quickly. But let's see if maybe there's ways to kind of get that. Let me just focus on first telling the basic story here. So we basically have this create an index I on doc using gin. So these I think are essentially the same thing. This is basically doing the same thing. But in this case here, I'm going to explicitly put it in, and in the other case, I'm going to actually these. I believe that's what I was getting at here, is that these will give you the exact same behavior. So if I go here and I actually go in and I put in a new column into the doc table. The doc table is this one right here. It's a very simple table. It's just got the ID and the actual text. But I add a new column, which is basically just going to wind up being the TS vector of the content. So it's actually just going to go and it's going to do the content. That is equivalent to doing this up here. That's I believe what I was getting at here. They're doing essentially the same thing. Okay. Now, if we don't have any indexes at all, and we run a query over a simple little database where I basically say Trump and presidents and tweeting, and then English content. Okay, and it's basically doing the content here. This winds up being 6 milliseconds in this very small database I did. But if you actually wind up using the index, so in this case here, it's doing the index was the name of the column I added. Yeah, if it uses that, then it collapses down to quite a bit less. And the reason why is pretty obvious. In this case here, if we just have the table, it's actually going to be going, and for each of the contents, it's actually going to be calculating and creating on the fly the text string vector. So what indexing does, it just goes through and it calculates the text string vector kind of beforehand, which is what you would want it to do, and you get significant savings. I'm not really that up on exactly how, like, let's think about it for a second. What you would want to do is you would want to do an index of indexes. I mean, the question is that what kind of games can you play around with to really speed this up? So for instance, let's say I have millions of documents and each document is fairly large, and I'm searching for a very obscure word called something like, say I'm looking for the word, it's not that obscure, but I'm looking for the word Tesla, right? It would be nice if, let's say I'm looking for the word Tesla and like, you can do more sophisticated things, or you can say Tesla followed by, where the same sentence is, Musk is in the same sentence or something. What you would want is you want to have it so that it uses an index so that it only touches documents in which Tesla appears. So it's not going through and looking at every single text string vector for every single oddball document in the world and saying, oh, there's Tesla in there. We would like to have it so that we have an index on top of the index somehow so that we can exclude that. I'm not really sure how you get that done, but that seems to be something that you want to get done. I'll look a little bit into that. But at face value here, what's happening is if I have 1,000 documents and I say, give me all the documents that have Tesla in it, then it actually has to look at each of these indexes that are in this table here and say, is Tesla in there or not? And then it can maybe very, very quickly determine if it's in there, but it would be nice to have it so that it even skip doing that. But I'm not really sure how you achieve that. All right, so the full text searching, I mean, it's kind of developed in PostgreSQL. I'm not sure. They probably have a lot of add-on packages that are doing it in a more sophisticated way. It didn't seem like it got like the full way to doing kind of probabilistic. It doesn't have the full capability of general natural language processing tools inside of it, but you can at least have it kind of supports this kind of Boolean stuff. And then you could probably kind of wing it to kind of get it to do a little bit of vector space model type stuff. So let's just kind of wrap it up here. Yeah, so this just kind of alludes to the fact that when you start getting into kind of full text search and kind of getting into a lot of kind of tricky issues come up, but sometimes you don't need all this stuff. I mean, the application is good enough just to do kind of single kind of word token search. But if you really want to do kind of complicated things, then you can get into kind of the more NLP side of things. So extraction is like text extraction has to do with like going through and having a fixed set of templates that correspond to like the tables in your database and extracting tuples out of the actual text document and then inserting them in. So things that you use for that are like Spacey and then a lot of machine learning techniques. So there's been a real innovation in terms of machine learning to kind of like guide these systems so they can do better jobs of extraction. So you really are going to be using like the knowledge-based approaches to this really have not fared very well. But maybe in very, very specific domains, you might still need to use them because there's always the issue of false negatives, false positives, and what's the sensitivity? I mean, in the practice, I mean, how tolerant is, I mean, a lot of times when you do NLP stuff, you basically have to say, all right, how robust or how sensitive is my system against false positives? Okay, answer that question. Fine. How sensitive is my system against false negatives? Right. So you need to kind of ask both those questions to kind of get a sense of what's going to be appropriate and how far are you going to go? What techniques are you going to use, basically? Document classification, yeah, classifies documents as into certain classes. So it's labeling the full document at the bulk. So sentiment analysis is a case of this. That's very amenable to machine learning methods. All right, so but you still again the false positive, false negatives. What techniques tend to emit more, less of those, and it's a trade-off most of the time. All right, question answering. All right, so from a text question, find a set of sentences, spans in a document that answer that question. So this is a big research topic. There's a whole field unto itself. So I load in all of the decline and fall of the Roman Empire, and I say, which emperor came in after Augustus? What was the first one after Augustus? That's a tough question to answer, but it probably could be answered with modern question answering techniques. It's probably in there somewhere. So there's a sentence that says, following Augustus, and then was Claudius, and Claudius did something or other. Or so immediately, there might be some sentence in there's a giveaway for that, but it might also be more complicated and might need to kind of pull together and do inference from the text. So it's very interesting, but it's very difficult. And then, of course, the false positives. Well, you can always have it so that you have no false positives by basically not doing anything, and you can always and you can have you have no false negatives by letting everything in. So there's kind of there's a trade-off there with that. But how you fit the question answering and all these other more advanced things into an actual database architecture is tough. I would say that in general, databases would like to say that things would be pre-processed, and so if you have something that's a result of pre-processing and then put that just kind of as an answer in the database, if you can do that, then that's probably the best way it gets integrated in. Question answering is very tough to do that with. Conclusions. Semantic. Okay, so let's just back off completely. This was kind of just a whirlwind tour of all this kind of other stuff, but this other stuff, of course, comprises most of the data out there. So conclusions: semantic web technology and or some other magical way to treat the web as a database are probably a bit of a pipe dream. But the NLP stuff might, it's a pipe dream, but it's you get little kind of wins here and there. It's difficult and tedious work to build up coherent databases based on data exchange and extraction, but it's doable. And so this is typically what actually will happen. The information retrieval methods, so that's kind of like the keyword search methods, are being brought completely into database, allow SQL to access IR. So it's kind of still in process, but those are coming into databases. And then the developments in NLP are offering great promise, and it's a very fast-moving set of developments. But it's definitely going to be there'll be impacts from that. Okay, yeah. So that concludes it. That concludes the lecture for today. And so I suppose if there were any questions, I would have seen them. Any other questions come up? Okay, I'll get the recitation published by the end of today on this. So we'll have, and then recitations in 1 week. I'll try not to put too much into it because I realize you guys are busy with your projects and stuff. So yeah, so we'll just do it that way. Okay, so if there are not any questions, then we can just adjourn. Okay, I'll stop recording.